lesson 1 of part 3 of energy, and this is looking at something called specific heat capacity. We need to look at what that means, and we need to be able to use an equation to allow us to calculate it. So the first thing we needed to look at was to consider the situation where we have two Bunsen burners. They're both identical. We've got two identical beakers, but one beaker has got 200 centimeters cubed of water. The other beaker has only got 100 centimeters cubed of water. Which one will boil first and why? Now, most people can answer this question pretty simply with something saying beaker 2 will boil first. Why? Because it has less water. So this is beaker 1 and that's beaker 2. And that sort of intuitively makes sense to people. So we can put this in more precise language, and we can say that the beaker with a smaller volume of water requires less energy to make it boil. So why does it boil first? Because we don't have to heat it for as long. It requires less energy to reach 100 degrees. Then we had, what if we had two beakers, both have got 200 centimeters cubed of water, and this time we're heating one to 50 degrees and the other to 100 degrees. Well, which one is hotter? Well, clearly that's the one that's 100 degrees. And which one has more energy? And again, most people would see this intuitively. Well, the one that is at 100 degrees, it's hotter, so it has more energy. So we have a number of things that we need to consider here, particularly the word heat and the word temperature. People tend to use them interchangeably, but they don't mean the same thing. So heat means precisely something to do with energy, and it means the total energy stored in a substance. Now, heat depends on temperature and mass. How do we know that? Because here we saw that to boil the beaker that had got twice as much water, we needed to put in more energy. So the more mass there is, the more energy we have to put in. And also we saw that one that was raised to a higher temperature will have more energy. So the amount of energy stored in a substance will depend on what temperature we put it to and how much of it there is. Now, temperature is not the same as heat. So heat is to do with energy. Temperature is specifically the measure of the average kinetic energy of the particles in a sample of matter. So kinetic energy is the energy something has because it's moving. So temperature is to do with how quickly, on average, the particles are moving. So it's an average of how much the particles are moving or vibrating in a sample, vibrating if it's a solid, moving if it's a liquid or a gas. And the more they are vibrating, the higher the temperature. Sure that you looked at the video carefully, or the PowerPoint I should say carefully, to get the examples where we saw that even when we put the same amount of energy on two substances, the change in temperature can be different. So a good example is on the beach during the summertime, and for the same amount of energy coming from the sun on both water and sand, the increase in the temperature of the water is quite small, but the increase in the temperature of the sand is very large. So for the same amount of heat energy, the temperature of the sand is increased by more than the temperature of the water. Remember what that means is that the average kinetic energy of the particles in the sand is increased by more than the average kinetic energy of the particles of the water. Now, why is that? That's because of something called specific heat capacity. So specific heat capacity tells us about the capacity that a substance has to absorb and store heat energy. So, for example, water has got a much larger heat capacity than sand because it's able to absorb much more heat energy before the temperature is increased. So we can define this exactly in precise words, where we say the specific heat capacity is defined as the change in energy needed to raise the temperature of 1 kilogram of the substance by 1 degree. So for example, we are saying that to raise the temperature of 1 kilogram of water by 1 degree, we'd need to put in much more energy than to raise the temperature of 1 kilogram of sand by 1 degree. So we can calculate this by using the following equation. The change in thermal energy is equal to mass multiplied by specific heat capacity multiplied by temperature change. Symbols as written as delta E. This triangle means change in, so the change in energy is equal to mass M times specific heat capacity, which is C, times the change in temperature. So again, we've got the change in, and temperature is represented by theta, this Greek letter. So the symbol for change in thermal energy is change in E, delta E, and it's measured in joules, which is shown with a capital J. The symbol for mass is M, and it's measured in kilograms. Symbol for specific heat capacity is C, measured in, well, we've got joules, kilograms, and the temperature. So it's joules per kilogram per degree. And the symbol for change in temperature is delta, and it's Greek letter, and it's measured in degrees. Next thing you were asked to do was to rearrange the equation for the change in thermal energy to get the equation for the change in temperature, for specific heat capacity, and for mass. So these rearranged equations are shown. Remember, the symbol is what we use to replace the word. So for example, the word mass we replace with M. The word specific heat capacity we replace with small c. And you need to be able to rearrange the equation if needed. Now in this equation, the tricky part when you rearrange is you need to make sure, especially when you're using your calculator, that you don't forget, for example, that the change in temperature is the change in energy divided by the product of the mass by the specific heat capacity. So you need to make sure that you're dividing by these two multiplied together. Okay, so we're going to practice some questions, and as always you need to show all 4 steps. So remember, the 4 steps are: step 1, to write out all the numbers, and you must make sure you write the word or the symbol beside the number. So I've got specific heat capacity is equal to 4,200 joules per kilogram per degree. Mass is equal to 750 grams, and I should remember that the mass has to be in units of kilograms, so I need to convert grams into kilograms by dividing by 1,000. And the change in temperature, well, I'm told the start and the end temperature, so the change in temperature is going to be 91 minus 34 to give 57 degrees, and I'm looking for the change in thermal energy. Then step 2, I write out the equation. Step 3, I put the numbers in the equation. So I've got the change in energy. It's equal to 0.75 times 4,200 multiplied by 57. And I put that into my calculator and I get the answer. Now make sure you complete the other 2 questions with all 4 steps. Okay, so here we have the other 2 questions. Make sure you pause the video so that you can check your answers, and watch out for where I've done conversions, for example here, and where the equation has had to be rearranged to see how that worked. Next task, you had to look at a video which showed an interesting experiment, so that a balloon, if it's just filled with air, if we put it over a flame, it will very quickly burst. But if we fill the balloon with water, then we can hold the balloon over the flame and it doesn't pop. And the question is, why doesn't this happen? So what's happening is the specific heat capacity, remember, of water is very high. So water has got a very large capacity to absorb heat. So in the case where there is water in the balloon, the heat from the flame, which is heating the surface of the balloon, is absorbed, that energy is absorbed by the water, which doesn't increase its temperature very much, and the warm water will move away, being replaced by cool water, which will then absorb more of the heat. And it won't be until a large amount of energy has been transferred, absorbed by the water, to raise the temperature sufficiently to cause the latex of the balloon to burst. When the balloon is only filled with air, air has got a very low specific heat capacity, so it doesn't absorb very much of the heat energy. So the balloon, surface of the balloon becomes the temperature goes up, it becomes very hot and it pops. In terms of specific heat capacity, this works because the water inside the balloon has got a very large specific heat capacity. It can absorb a lot of heat energy. Okay, now next we had to look at some information and use that information to help us explain the statements. Okay, so first of all, we're showing this table and it has the specific heat capacities for different substances. And it says a mass of lead heats up more easily than the same mass of aluminium. And we're asked to explain why that is. So what we can see is that in the table, aluminium has got a specific heat capacity of 900, whereas the specific heat capacity of lead is only 130. So lead is almost 8 times lower specific heat capacity than aluminium. So we can say that as, and by the way, heats up, that term heats up, what they mean is there is a lot, it's easier to increase its temperature. Okay, so what can we say? We can say as aluminium has a much larger specific heat capacity than lead, and we can calculate it. So it has 7 times larger specific heat capacity than lead. So it has a much larger specific heat capacity. It can absorb much more heat energy without a significant increase in temperature. Okay, so the other way that you can say this, as it was said in the PowerPoint, is that then to increase the temperature of the aluminium by the same amount as we increase the temperature of the lead, we need to put in much more heat energy. So that will take much longer, or we would have to have a more powerful type of heater for the aluminium. Then it says how much energy is needed for each of the following. So here we're going to use our equation, so we need to do our steps. To raise the temperature of 2 kilograms, so we're told the mass is 2 kilograms. We're looking to change the temperature by 30 degrees. We know that specific heat capacity is 900. So we can now work out what energy is needed. Remember, the change in thermal energy is mass times specific heat capacity times the change in temperature. So that will give us, putting in the numbers, 2 multiplied by 900 multiplied by 30. And I put those numbers into my calculator, and that gives me an answer of change in energy needed is 54,000 joules. Once again, using all 4 steps. So once again, using all 4 steps, writing the numbers out, writing the equation, putting the numbers in the equation, we get the answer. We need 8,400 joules of energy. The next question was actually a question from a GCSE paper. And often what you find in GCSE papers is there is a lot of writing at the start, maybe with diagrams, before you come to the actual question. So you have to be careful because there can be information in either the diagram or in the writing that you will need. So it says a student investigated how much energy from the sun was incident on the Earth's surface at her location. She put an insulated pan of water in direct sunlight and measured the time it took for the temperature of the water to increase by 0.6 degrees. And we've got a picture of what her apparatus looks like. Choose the most appropriate resolution for the thermometer. She wants to measure a change in temperature of 0.6 degrees. Well, if she had a thermometer that was 0.1, let's say she was starting at 0, it would go 0, 0.1, 0.2, 0.3, all the way up to 0.6. That one will work, so that one's okay. The next one's 0.5. Well, if we again started at 0, that would go 0, and then to 0.5, and then to 1.0, because its resolution is steps of 0.5. So she'll never be able to work out when it was 0.6, so that one's not going to work. And this one, we're in steps of 1, so it would go 0, 1, 2. So that one won't work either. So the only one that will work is this one. Then the next question says the energy transferred to the water. So we're told how much energy was transferred. We're told how much time was taken, 5 minutes. Note the minutes. And we're told the specific heat capacity of water is 4,200 joules per kilogram per degree. And they've asked us to write down an equation that we should be able to recall. And that equation is, what is the equation that links energy transferred, power and time? So we've got the energy transferred equals power multiplied by time. Power is how much energy we're transferring to something every second. So energy transferred is equal to power times time. Calculate the mean power supplied to the sun. Well, what were we told? We're told that the energy transferred is 1050 joules. We're told that the time is 5 minutes, but this needs to be converted into seconds. So that's going to be 5 multiplied by 60. So I use my calculator. I get an answer of 300 seconds. And we're looking for the power. So I'm going to use this equation, so it gives me 1050 is equal to the power multiplied by 300. So that gives me the power is equal to 1050 divided by 300, an answer of 3.5 watts. The units for power are watts, shown with a capital W. Then we've got calculate the mass of water used in the investigation. So again, let's see what information we're told. We're told what the energy is. We're told the time. We're told the power. What else are we told? We're told the specific heat capacity of water. We're told how much the temperature has changed by, and we want to find the mass. So from these numbers, we need to know which equation can be used that's got mass in it, and the equation we can use is the one that we've been using up to now. And we can substitute the numbers in. So we've got 1050 is equal to the mass multiplied by 4200 multiplied by 0.6. So that gives me the mass is equal to 1050 divided by 2520. So the mass is equal to now 0.41666667, or so how should I write this? I do not I do not write it with recurring. Never use the recurring. Here I've got 2 significant figures there, 3 significant figures here. So I can choose to use either 2 or 3 significant figures. I'll choose to use 2, so that would give me the mass is equal to 0.42 kilograms. If you're not sure, always use 2 or at most 3 decimal places, never more. So energy part 3, lesson 2. And to start, we're asked to answer this question. Again, this is a GCSE question, so we've got a lot of information given at the start that we may have to refer back to as we're going through the questions. And the first question is asking us to work out the change in thermal energy during this experiment. And in the second part of the question, it's asking us what variables would need to be controlled. So for the first part, we're going to use our all 4 steps as we always do. So here I've got my numbers written out. I've got the change in the temperature was 11.5, 31.5 minus 20 from the table. And we're asked to work out the change in thermal energy. So I'll put into the do my steps, write down the equation, put the numbers in the equation, calculate the answer. However, one thing we need to be careful of is it says give your answer in kilojoules. So I need to convert from joules to kilojoules. And we go from any unit, meters to kilometers, grams to kilograms, joules to kilojoules. We divide by 1,000. So change in thermal energy is 15.525 kilojoules. It would also be correct to write that as 15.53. Would also be correct. The second part, we're asked to talk about control variables, things that the students would need to keep the same if they redid the experiment. Well, there's some obvious ones they need to keep the same. We're talking about specific heat capacity. So a really obvious thing that we need to keep the same is we need to have the same material, because the specific heat capacity changes if we're using a different material. Also, we saw from lesson 1, the amount of energy that we have to put in will depend on the mass. So we need to have the same mass. Then we can think of, well, we're putting energy in, we're assuming that all the energy is used to raise the temperature of the block. So none of the energy is being wasted. So we need to have the same insulation so that the same amount of energy is being used as much as we can to increase the temperature of the block. And when we say the same insulation, that means, again, the same material and the same thickness of material. So these were the obvious ones, same material, same mass. This is also an important one, but it's a sort of a secondary one where we're talking about we want to have the same, or to have the same amount of energy wasted when we do the experiment a second time. And then we could have the same starting temperature and we could have the same current in the heater. Now the next task you needed to do was to plan an experiment to investigate the specific heat capacity of a metal block. And whenever we're looking to plan an experiment, we always start with our hypothesis and prediction. What is the science underlying our experiment and what do we expect as our result? What are the independent, dependent and control variables? What are we going to change? What are we going to measure? What are we going to try and keep the same? And then we need to come up with a method, a plan. And one thing I would suggest that you do is this document you can Google. AQA is the board that you're using for your science. And if you Google AQA GCSE Physics Required Practical Handbook, all of these required practicals are described in this book, including this experiment on specific heat capacity. It will gives you a method and it gives you some example results. So it also has both the document for the teacher, and it has a complete method that you would be given doing the experiment in class. So this is a really useful document, and I would suggest you download this from Google. So you need to make sure that you've watched the video that was in the PowerPoint. So in terms of the hypothesis, the science underlining our experiment, we're looking at the specific heat capacity of a metal block. And what the science we've looked at so far says that the amount of thermal energy that we need to put into a substance is equal to the mass of the substance times specific heat capacity times the change in temperature. So what we can say is that if the amount of energy is increased, the temperature increases. Here we've got the amount of energy, and here we've got the increase in temperature. And we can say more than that because the mass and the specific heat capacity are constant. So this is an equation in the form y equals mx plus c. C in this case is 0. This is what's known as a linear equation. So in fact we can say the change in temperature is directly proportional to the energy. We would expect a straight line graph. We can then use that graph to be able to work out our value of specific heat capacity. Define the independent, dependent and control variables. Independent variable, this is the variable that we're changing. Obviously if we did it for more than one metal block, that would be the type of material, but we can assume we're just doing it for one block. So what are we controlling? And that is the amount of energy. And what are we measuring, which is the dependent variable? That is the temperature. And control variables, what are we keeping the same? Well, the nice thing about physics, particularly because it's often based on equations, is it's very easy to see what we need to keep the same from the equation. So one of the things we need to keep the same is the mass. So one control variable is the mass that we need to keep the same. We could also have, for example, the starting temperature we need to keep the same. Okay, and then we need to identify the equipment and include a diagram. So here we have the practical described for us. We're told the apparatus. Here we're doing an experiment with different metal blocks. We need some insulation to wrap around the metal block, a thermometer. We need something to provide the heat energy, which is what's called an immersion heater connected to a power supply, an ammeter and a voltmeter, and we're going to see why we need those in a moment. Some leads to connect it all together, a stop clock and a balance. Remember, we measure mass with a balance. So then in terms of the methods, first of all, we measure and record the mass of the block, and we make sure we record it in kilograms. Put the insulation around the block, place in the heater, connect the circuit together, and the ammeter and the voltmeter are measuring the current through the heater and the voltage across the heater. Then we put the thermometer into the block as well, switch the power on, and we record the ammeter and voltmeter readings, measure the temperature and start the stop clock. Then record the temperature every minute for 10 minutes, recording the results in the table below. So you can just, the easiest thing would be to search on Google and download the document. You can also pause the video so you can see the method written. And on the other page, like this. Now what's interesting here is when we do a table, the leftmost column, this is always the independent variable. This next column, this is my dependent variable. So I write independent variable in the first column, In the next column, it's got the thing I'm measuring, in this case, the temperature. Now, we said that the independent variable was the amount of energy. We're not measuring that directly, so instead of this, we have the time in seconds, and we have the power of the heater, and we're going to use that information, as we'll see, to work out the amount of energy in the experiment. Okay, now in lesson 3, we have the actual investigation described. So we're given the method, and again it says that you need to highlight any details that you were missing in your part in lesson 2 of the pack. So it gives us what the experiment's about, gives us the apparatus, it shows us the diagram, and gives us a table of results, the method, and the table of results for the change in temperature. So it then describes what it is we need to do to be able to work out the specific heat capacity of the material. So what we need to do is complete the analysis, plot a graph, and compare the value, the specific heat capacity, to the expected value. Okay, so first thing we need to do is, on this page, we have the material aluminium. We're told that the mass measured is 1 kilogram. We're told that the potential difference is 12 volts and the current is 6.25. And we need to get the power. And to get the power, it's simply the potential difference multiplied by the current. So in this case, the power is 12 multiplied by 6.25. That equals to 75 watts. So the power of my heater is 75 watts. Now the next thing we need to do is, so that was the first thing we need to do, is calculate the power of the heater in watts, and we've done that thus far. Next thing, calculate the energy transfer. To do this, multiply the time in seconds by the power of the heater and record the values in the table. So just for convenience, I'm going to write above here, the power is equal to 75 watts. That's what I worked out. So what I need to do is multiply this by the amount of time. So I've got 75 multiplied by 0, so that's 0 joules for the first one. And then I've got 75 multiplied by 60, so that is 4,500 joules. And I'm just going to complete these, and you may pause the video then to check your answers. So these are all the values for the change in thermal energy needed to increase the temperature by the amount shown. Maybe that you've had to draw on plain paper, you've just drawn a graph as best you can. And the most important thing about a graph is that we have the two axes. We have the axis clearly labelled, work done in joules. On the x-axis, temperature. On the y-axis, remember, this is the independent variable. This is my dependent variable. And what I was saying was, our equation was that change in thermal energy is mc times the change in temperature. So we can see that this is a linear equation, so we expect a line. Now they do say in the notes that we need to take care, because the start of the graph is often curved. So this is what we see here, where there's a small change and a little bit at the end as well. So what we're looking to do is draw a line of best fit, but I'm going to ignore pretty much these first couple and the last point and really concentrate on these values in the middle for my line of best fit. Okay. The other thing to be important about a graph is it should be as large as you can make it. So you choose a scale to make it as large as you possibly can. Okay. Then we say calculate the gradient of the straight line. So the gradient, and I say the gradient is equal to the change in temperature over the change in work done. So to get the gradient, what I need to do, and I can pick any point on my line, try and make it as easy a point to use as I can. Let's say from this point up to this point. Okay, so and that's there. Okay, so here I've got, this is my change in temperature, and this is the change in energy. We know that for the gradient, we know from maths, the gradient is equal to the change in y, the change in x, so that's equal to the change in the temperature divided by the change in energy. So what's my change in temperature here? I'm going from 22.5 degrees all the way up to 57 degrees. So my change in temperature is 34.5 degrees. And my change in energy, I'm going from 5,000 joules here up to 36,000 joules. So I have the change in energy is equal to 31,000 joules. So my gradient, change in y over change in x, that's equal to 34.5 divided by 31,000. So the value I've got for the gradient is equal to 0.011. Remember, units are going to be per joule. Okay, now it says the heat capacity is calculated using the formula 1 over the gradient. Okay, so to get the heat capacity, my gradient I discovered was 1.1 times 10 to the minus 3. So therefore my heat capacity is equal to 1 over the gradient (898.6 joules per kilogram degree C). Okay, so the specific heat capacity if it was copper, is the amount of heat energy in joules needed to increase the temperature of 1 kilogram of copper by 1 degree. So in this case, we don't have copper, it's actually aluminium, and our specific heat capacity we've worked out is 898.6. So we can work out the value for aluminium. And the next thing it says, compare the value to the expected value. So my value, C, is equal to, and I'm going to round this to 899 joules per kilogram degree C. The expected value, well, if you didn't have an expected value, this is where Google comes in useful, you would Google a value and you put in a reference then to say where you found it. But fortunately, we did have a question at the start of lesson 2. I beg your pardon, at the end of lesson 1, where it gave us the specific heat capacities for different things. And we see we've got aluminium here. So the specific heat capacity we expect is 900 joules per kilogram. So this answer, I'm only 1 joule per kilogram per degree away from the expected value. So I've got a very accurate answer. Then finally, it says evaluation. How could the experiment be improved? Discussing any potential sources of errors and how these could be minimized. So what I'd like you to do here is make sure you've gone back and you've looked at that video that was attached to the PowerPoint to make sure that you've looked at what was described about possible sources of error. The first problem is some of the energy that we were passing through the metal block from the heater, it may actually have been dissipated to the surroundings. We don't have a fully efficient system, so some energy is wasted. And that could be because the heater isn't fully immersed inside the block, or that we don't have very good insulation, so that we're losing some of our energy to the surroundings. So how can we deal with this? We make sure that we have good insulation around the block and with low thermal conductivity, which we saw in the previous part of the energy topic, and the heater fully immersed in the block so that it's completely inside the block. We could have also inaccuracies with our reading of the temperature or the reading of the mass. So we could have inaccuracy due to misreading the mass, the temperature, and we can overcome that, use electronic balance for the mass, an electronic temperature probe, and if we link that to a data logger, then it avoids the problems that can happen when people write down the wrong result. Okay, so that was the third part of the energy topic. Make sure that you have fully corrected your pack and then complete the exam questions.